What is the difference between the process and the thread? This is a common question, so let's take a look. To better answer this question, let's first understand what a program is. A program is an executable file. It contains the code or a set of processor instructions that is stored as a file on a disk. When the code in a program is loaded into memory and executed by the processor, it becomes a process. An active process also includes the resources the program needs to run. These resources are managed by the operating system. Some examples are process registers, the program counters, stack pointers, memory pages assigned to the process for its heap and stack, etc. There is an important property of a process that's worth mentioning. Each process has its own memory address space. One process cannot corrupt the memory space of another process. This means that when one process malfunctions, other processes keep running. Chrome is famous for taking advantage of this process isolation by running each tab in its own process. So when one tab misbehaves due to a bug or a malicious attack, other tabs are unaffected. Now let's look at the process states. First, we have the new process, where the process is being created and is ready to be assigned to the memory. Then we have the ready state. Here the process is waiting to be assigned to the processor to start executing. Then we have the running state. Here the program and its instructions are being executed in the processor. From there on, we have three possible outcomes. Either the process finishes execution, which is called the terminated state, or it goes back to the waiting state, waiting for some event to occur, like the input-output instructions, or the process is temporarily interrupted, which can happen when a high-priority process is being executed at the same time. Thread. So what's a thread? A thread is a unit of execution within a process. A process has at least one thread. It's called the main thread. It is not uncommon for a process to have many threads. Each thread has its own stack. Earlier we mentioned registers, program counters, and stack pointers as being part of a process. It is more accurate to say that those things belong to a thread. Threads within a process share a memory address space. It is possible to communicate between the threads using that shared memory space. However, one misbehaving thread could bring the whole system down.
And now let's recap and make comparison between process and thread. First, process is known as a program under execution. On the other hand, thread is a small segment of a process. Second, process is a heavyweight process and thread is a lightweight process. This makes sense because we know that thread is a small unit of a process. Third thing is process takes more resources like memory usage. Each process has its own address space, which means that it has its own copy of the program code and data. This can lead to higher memory usage than threads, which can share memory with each other threads in the same process. Fourthly, context switching takes more time in process than thread, because when computer switches between processes, it must save and restore the state of the entire process. This can take more time and resources than switching between threads, which only requires saving and restoring the state of individual thread. Fifth, communication in process slower than thread, because in process involves copying data between different processes, which can introduce additional overhead in terms of CPU usage and memory usage. This can slow down communication between processes, compared to communication between threads, which can share memory directly. Finally, because of these things, process needs more time for work and conception more than thread. User thread. They are created and managed entirely by the application or user-level library, rather than the operating system. Kernel is not aware of the existence of these threads. It handles them as if they were single-threaded processes. They are typically faster to create and manage than kernel-level threads, because they do not require system calls to create and switch between threads. The thread library contains APIs for creating and storing threads, for passing message and data between threads, for scheduling thread execution, and for saving and restoring thread contexts. Kernel thread. They are created and managed by the operating system kernel, which provides built-in support for thread creation, scheduling, and switching. Kernel threads are generally slower to create and manage than user threads. Because of these reasons, they are generally more heavyweight than user-level threads, because each thread requires its own kernel-level data structures and system resources. User versus kernel. Both kernel threads and user threads usage depends on specific requirements and constraints of the application. Here are some examples of how kernel and user threads can be used. Kernel threads are well suited for tasks that require low-level system access, such as device drivers, network protocols, and file system operations. On the other hand, user threads are more lightweight and efficient than kernel threads, as they do not require the same level of the operating system support. Kernel thread can handle blocking input-output operations efficiently, as they can be put to sleep by the operating system and awakened when the input-output operation completes. On the contrary, user is well suited for applications that require a large number of threads, such as web servers or multimedia players. Kernel can take advantage of multiprocessor systems and distribute the workload across multiple cores, improving overall performance. On the other side, user can be implemented entirely in user space, which makes them more portable and easier to maintain across different platforms.
Dividing program. And now let's move to the final topic, which is program dividing. A process may create several new processes via a create process system that is called during the course of the execution. The creating process is called the parent process, and the new processes are called the child of that process. The parent process creates a new process by calling the system call, such as the fork. We've seen that a program is made up of several processes, not just one process. And of all these processes, not all of them are made individually. Some are made from a single process. The create process system call can be called during the execution, and several processes can be made from one single process. Each of these new processes may in turn create other processes, forming a tree of processes. But why would we divide a program into more than one process? Let's see. The first reason would be if a program wants to run an additional instance of itself. Like a web server, where it receives the request, creates the additional instance of itself to handle the request. On the original instance, it continues listening for requests. Or the second reason, where the program wants to run a different program. The program may rely on other programs or libraries to function properly. For example, a program that uses a database may need to run database server in the background.